reaching 100% functional coverage using machine learning, a journey of persistent efforts. Abstract. With the increasing complexity of IP-RTL design, it can become more difficult for design verification engineers to achieve the functional coverage closure based on a constrained random verification. This is one of the critical factors in delaying verification time. To address this issue, this paper proposes an automated functional coverage closure technique using machine learning and present various strategies to enhance the accuracy of the machine learning model's predictions, enabling quick filling of the functional coverage holes. This technique focuses on cross coverage, utilizes a Python-based coverage agent. The proposed technique was evaluated by applying it to the camera serial interface (CSI) design, so which is a part of the image signal processor ISP blocks in mobile SoC and achieved the functional coverage closure significantly faster than the baseline without much effort from the DV engineer. Chapter 1 is product introduction. IP-RTL designs are becoming increasingly complex to meet market demands on enhanced features. This complexity makes it more challenging for design verification engineers to achieve the functional coverage closure based on the random constraint verification. So this leads the DV engineers to demand more effort and painful functional coverage closure. Moreover, it's one of the critical factors in verification turnaround time (TAT). Many DVCON papers related to functional coverage closure support these facts 1, 2, 3. These papers demonstrate how to generate meaningful test stimuli and vast input spaces to achieve faster and low effect functional coverage closure through various approaches. In this regard, the study aligns these previous works and present a different approach. The cross coverage when creating a functional coverage model involved any combination of more than two variables or previously declared coverage points. It helps to verify if the behavior of the specific combination of the device under test (DUT) is covered in the test. According to our experience, when the number of tests increase during functional coverage measurement, each cover point defined in the coverage model is easily filled. But cross coverage, which is made up of the combination of cover points, is often not well filled. To address the cross coverage beams that are fully filled, the DV engineers may analyze the coverage results generated by the tool, run closely related scenarios more intensively, adjust the distribution of related configurations, or assign certain values directly. Regardless of whether there are other methods in addition to those mentioned, analyzing the result and taking actions requires a significant amount of effort and time from engineers. Based on our heuristic approach, we identified cross-coverage measurement 2 as a major factor contributing to the functional coverage closure challenge. This study analyzed the causes why cross coverage is not well filled and proposed an automated functional coverage closure using machine learning, which is focused on cross coverage and introduced a Python-based coverage agent that supports this workflow. This paper also showed the use of various strategies to apply machine learning model prediction to enhance the accuracy of prediction. This ultimately leads to gradual increase in the confidence of the outcomes created by the coverage agent to fill functional coverage hole. These results allow the functional coverage to fill aggressively and quickly without the intervention of the DV engineer. This approach was evaluated by applying it to the camera serial interface (CSI) design, which is part of the image processing processor ISP block in a mobile SoC. As a result, the proposed approach achieved functional coverage closure substantially faster than the baseline without much effort from the DV engineer. So chapter 2 is background. In this section, we analyze why cross-coverage beams are not well filled in when measuring functional coverage through several experiments. To achieve this, we declare the four random variables test A, B, C, and D as shown in figure 1a, and made them have an equal weighted distribution. These variables have 2, 6, 5, and 7 possible values respectively. Therefore, the cross-coverage cross underbar test underbar ABCD consists of a total of 420 beams. Figure 1b shows the result of the 5,000 randomization of these random variables, with this x-axis representing the frequency and which each combination of the random variables was generated out of the 5,000 trials and sorted in the descending order along with the x-axis. The graph displayed an uneven distribution contrary to expectation. Even though the probability of distribution of random variable is equal, there is significant difference between the maximum value 25 and the minimum value 3 of the frequency distribution, as evidenced by figure 1c. This is because the number of runs, 5,000, may not be large enough. Figure 1. Result of 5,000 randomizations when the weighted distribution is uniform. What would happen if one of the four variables had a different weighted distribution among them? Figure 2 illustrates how the mean and max values of the frequency distribution of cross-coverage combination vary as the distribution of a test underscore A changes. It can be observed that as the imbalance in the values of the test A increases, the difference between the mean and max values of the frequency distribution also increases, and from a ratio of 2 versus 8, it can be seen that certain combinations are no longer generated. Although not indicated in figure 2, there were 3 combinations that were not generated for the 2 versus 8 case, 2 to 8 cases, and a 20 combination for the 1 to 9 case. Figure 2 result of 5,000 randomization where the weighted distribution is non-uniform. But from these results, we can see even if the probabilities of the values that random variables can take are made equal, a very large number of repetitions are required for the mathematical probability intended by the engineers to be achieved. If the weighted distribution is not even, an even larger number of repetitions may be required. However, the biased weighted distribution can be intentional on the part of the engineers or occur unintentionally due to the complex random constraint. These results help us understand why simple repetition of the simulations does not fill the errors, does not fill the cross-coverage beams well, and these causes ultimately make it difficult to achieve functional coverage closure. Chapter 3. Suggested approach with example. This main idea of this study originated from the observation that cross-coverage cannot be easily achieved when measuring functional coverage, but individual cover points can be easily filled, as mentioned earlier. Cross-coverage is made up of a combination of cover points, each of which is composed of expressions or variables to be covered. If the cover points are guaranteed to be composed of random variables, and the cross-coverage is composed of these cover points, then the cross-coverage can be controlled through random variables. The relationship between them will not best known by the DV engineers who created them. But if a third party can predict these relationships without any help from the DV engineer, they can fill the cross-coverage hole instead of a DV engineer. So for this purpose, the coverage agent was developed a third party, leveraging a machine learning algorithm to predict the relationship between the cross-coverage and constant random variable. Selected the test and generated the random variable to fill the coverage hole. In this section, we illustrate the key concept techniques of the proposed approach using a simple constraint random variables of functional coverage model. The example code is further details in Figure 3. This helps to clarify the theoretical base and practical application of the proposed approach. Figure 3 is simple constraint random variables and functional coverage example. A. Example code analysis. In Figure 3a, there are total of 13 random variables along with the test x and test y have a non-uniform distribution. Figure 3b has assumed the combination of IP behaviors controlled by these random variables and includes functional coverage code and that covers them. There are a total of 8 cover points and 2 cross coverages declared. The variables starting with the name dummy are not used in the coverage model. So the table 1a shows the changes in the coverage rate for cross coverage when running the example code with 1000 iteration of regression. As explained in section 2, even though the cross-untested mode has a uniform distribution, it requires about 6,000 to 7,000 tests to fill 720 bins. In the case of the cross-tested XY with a non-uniform distribution, even with 10,000 tests executed, it does not fill all 2,688 bins. Although not shown in the table, when cross-test XY was run continuously without adjusting the weighted distribution of constraint or setting the directed value, it reached 99.74%, 2681 over 2688, after about 25,000 tests. On the other hand, Table 1b showed the coverage rate for the cover point of the first regression run. Unlike a cross coverage, it comes in that CP underscore test underscore X and CP underscore test underscore Y, which have a biased weighted distribution, also fill up easily like other cover points. So Table 1, the coverage result after result in the example code with regression. Type B is types of input for prediction. Figure 4a simply shows the overall workflow of the suggested approach and inputs and used in each step. In this paper, the version manager, hereafter the vManager, was used to run a regression test, and the integrated metric center, hereafter IMC, was used to merge the coverage result in a generated report. Figure 4, the suggested approach overview and coverage agent workflow. After the initial regression run, a row and coverage report and a coverage database for each test are used in input for the coverage agent. The row contains information about counter random variables as illustrated in Table 2a, which were printed using the UVM underscore field underscore star macros within the UVM object utils macro block in UVM. Based on the example code from Figure 3. After registering the random variables with the UVM macro, the variables are printed in a single line as shown in Table 2 to make them easier to parse. In addition to the ensure that all variables are printed without omission, we assign -1 to those dot begin underscore elements. Table 2 is a UVM code snippet for printing random variables in the blog. So the coverage report includes the functional coverage measurement result for each test, and which were created by the IMC. This is a tool of the cadence for coverage, incisive metric coverage. For instance, Table 3 examines a part of one of the coverage reports generated for each test using the example code from Figure 3. In coverage report, we can see the name of the cross coverage, the total number of bins, and current numbers of touched bin. We can also determine the number of cover points that make up the cross coverage, and this example, the cross coverage named cross test XY consists of a total of the 2688 beans, with only one beans being touched. By examining the B asterisk B asterisk B asterisk of the cross test XY, we can confirm that it's composed of 3 cover points. This means that 3 random variables are correlated. This information is crucial in determining the number of random variables needed to fill in the cross coverage through machine learning algorithms. Table 3, the coverage report example. Finally, the coverage database of each test are used to generate the overall coverage report. The coverage agent monitors that V manuals their operation upon completion of a session, merges the log and coverage report of each test in a CSV file named for config.csv and tabular data structure in Python, and subsequently merges the coverage database of each test and generated the 5 overall coverage report. These 2 files serve as the basis of the machine learning-based data analysis in the next step. C. Decision tree algorithms. Machine learning algorithms are used to predict which random variables should be controlled to fill the hole in a certain cross coverage. The selection of machine learning algorithms is crucial to reach measure characteristics affecting each performance and stable suitability for specific tasks. The decision tree is used in this study because it is one of the white box machine learning models. It allows us to understand how each feature contributes to the prediction and how important they are in determining the prediction. In this paper, the features corresponding to random variables and the target that the model needs to classify are numbers that are assigned to each cross coverage bin. Machine learning will predict the number assigned to each cross coverage bin for classification, as shown in Table 4. The numbers assigned to the cross coverage can also have a value of 0, indicating that no bins of the cross coverage were touched in the corresponding test. So the Table 4, the machine learning prediction result according to the number of regression iterations. The main focus here should not on whether the machine learning correctly classified the bin number, but rather on identifying features that contribute most of the classification task. The features with a high contribution to the classification are random variables that are highly correlated with the cross coverage, and they are sorted order to the contribution and stored in list format. The Table 5 shows the result of predicting which random variables are highly correlated with each cross coverage using coverage agent data applies the detailed description of the example code in Figure 3 after learning it for each regression iteration. As the regression iteration progresses, the coverage agent identifies the top 3 and the top 5 random variables associated with each cross coverage, cross test XY, and cross test mode respectively. This approach is based on the predetermined number of random variables required for each cross coverage as outlined in the coverage report. To gradually observe the process, the coverage agent limited the maximum number of tests that can be configured for a regression suit for 1000. In the predicted result, random variables that are correlated with the cross coverage have been marked in color. First, looking at the cross test XY, we can see that in the first iteration, test X, test Y were correct, but the related dummy I was predicted, and the next iteration, dummy 1 disappeared, but another unrelated test mode is predicted. And by the third iteration, it showed that the 3 random variables related to cross test XY are found correctly. Since the prediction was successful, if the number of tests configuring the regression was not limited, cross test XY would have been covered in third iteration. However, since the number of the bins that were not covered was greater than the number of tests, the next iteration was carried out. An interesting fact is that next iteration, it was wrong again. This change is analyzed to be due to the fact the input features random variables in target cross coverage numbering values of machine learning algorithms are selected randomly every iteration. Cumulatively, 80% of the data is used for training, while the 20% of randomly selected for evaluating the model accuracy. However, as previously mentioned, our focus is not the accuracy of the prediction, but rather on identifying the features that were considered crucial in arriving at the correct region. So in the end, prediction was successfully again in the next iteration and regression for cross-test XY was completed as the cross coverage was filled. Next, for cross underscore test underscore mode, it succeeded in the prediction in the second iteration, and since the number of the cross coverage being that were not filled was smaller than the limited numbers of tests, it was covered and terminated. Table 5 is the machine learning prediction result according to the number of regression iterations. In the simple example code, the coverage agent found in the random variable related to each cross coverage out of 13 random variables. However, in the case of the IP used in this paper, about 7,000 random variables were used for verification, and among them, the coverage agent needs to find the random variable related to each cross coverage. D. Utilizing machine learning prediction. The decision tree algorithm, one of the machine learning algorithms, have been explained in detail, including how it predicts and what it predicts. It is important to determine how to utilize these predictions. The random variables predicted by the machine learning are used to calculate their product set. The value of the random variables will be unique values for values that have been obtained so far while running the test. For example, in the case of the cross-test XY, Table 6 shows the result of calculating the product set the coverage agent successfully predicted in the third iteration of Table 5. So in the cross-test XY, the total number of the bean matched numbers of combination in the table, we can see that each combination is being counted to see if it's been generated before. Based on these results, the coverage agent reflects the combination that have not been generated in the next regression. So this approach is aggressive because it's an all or nothing strategy. If the prediction is successful, it will quickly fill the win. However, the prediction fails, the value will be entered into combination of unrelated random variables. Despite this disadvantage, the meaning of regression offsets by test valid as combinations. Even if it fails, it's like learning the regression as usual. Additionally, it's even luckier than the usual regression, where other cross coverage may be touched. This is the primary reason why machine learning with uncertainty and prediction can be applied to coverage for verification. This method assumes that all possible values of random variables should be generated at least once, and that the coverpoint coverage is easily filled. Therefore, this method does not consider cases where a coverpoint never fills up. So if the random variable is not uniform, the coverpoint fills late, the performance of the coverage agent will be affected by ultimately it will find the cross coverage hole. So table 6 is random variable product set for a cross coverage cross underscore test underscore xy. In this case, where the values of the random variables created based on the product set are combinations that cannot be produced by the constraint, what happens? Since the coverage agent does not know the constraint of the random variables, if it puts the unilateral combination of the number of cases for the next regression, randomization can fail. To eliminate this situation, all values of the random variables created by the coverage agent are declared as soft constraint, as shown in the table 7. These values will be assigned to each the test using the randomized web constraint block. Table 7 shows the random variables are declared as soft. Therefore, if an invalid combination is assigned, it will be ignored, and the random variables will be generated by randomizing them as usual without fail. In this case, it will simply become one of the regression tests and will be used as a data for next prediction. So E, coverage agent. The coverage agent, as mentioned earlier, is developed by using Python to process files, generate constant variables using machine learning, select a test, and create a new regression suit. Figure 4b simply displays the workflow of the coverage agent after waiting for the vManager to complete regression session. It parses the aforementioned files, merges them, and checks if the functional coverage 100% through the over coverage report. If it is not 100%, it analyzes the coverage, creates a regression suit, and then runs the regression again. The regression is executed in the batch mode, and then the subsequent step, summarizing, is carried out. And this step, the information about which cross coverage remains, how much is filled, and which random variables are predicted to be related to cross coverage is summarized and saved as a file. These files allow DV engineers to check the current functional coverage status and ensure that the process is running properly. And figure 5 below shows the result of applying the coverage agent to example code in figure 3, both graphically and in table form. A total of 4,378 tests were run with maximum of 1,000 tests per iteration, and 5 regression suits were executed. After the initial 700 test regression, the coverage agent was applied. In iteration 3, we can observe a significant increase in cross-test XY from 57.66% to 94.78% due to the successful predictions as shown in figure table 5. However, since the number of test examples per regression is limited to 1,000, it does not reach 100%. In this iteration 5, it successfully predicts again and shows the coverage rate of the cross-test XY reached to 100%. So in the iteration 4, the prediction failed, but as mentioned earlier, it's similar to performing a normal regression, so we can see the numbers increase. These accumulated 4,279 tests help the coverage agent make a more accurate prediction for next iteration 5 regression. In the case of the cross-test mode, it succeeded in predicting the second iteration and immediately confirmed that all coverage bins were covered. So now the figure 5 is the result applying the coverage agent to the example code in figure 3. The F, various strategies. The result in figure 5 shows the ideal behavior of the method proposed in this paper. It seems as if having more data too long will always lead to better predictions. However, in reality, this is not always the case. In theory, when prediction fails and regression is executed, the test information from the regression is used as training data to improve the model's prediction accuracy in the next step. In other words, cross coverage that continue to miss will gradually increase its probability of being correct as it progresses to the next step. In practice, however, the situation is not straightforward. The Accumulation of training data may sometimes lead to the model to enforce an incorrect prediction rather than correcting them. At this point, we describe the various cases encountered while applying this approach and explain the strategies that were introduced to address them. Case 1. When the model prediction list is shorter than the number of random variables related cross coverage, the solution is simple. Since this is due to the insufficient information in list of the tests that have touched at least one cross coverage and randomly selected them and put them back into regression suite. For instance, table 5, the cross test mode requires identifying the 5 random variables. However, if there is a lack of training data, meaning the insufficient numbers of tests, it's possible that the number of random variables identified through the machine learning algorithms may be inadequate. In such a situation, when the training data is insufficient, the coverage agent searches for scenarios related to target to the cross coverage and increase the number of tests for those specific scenarios. Case 2. When the model makes incorrect prediction and generates a product set of completely unrelated constraint variables, by chance or possible cases of these variables are covered. So for example, in table 5, there is a higher likelihood that prediction will be inaccurate due to the fewer test repetitions performed during iteration 1. The provided code examples was straightforward, so it quickly accessed test X and test Y, which are highly correlated with cross-test XY. Table 8. One of the worst case scenarios in the event of the prediction failure. However, in reality, finding the correct answer among numerous random variables is not an easy task. In the provided code example, let's assume that a cross-test XY prediction at iteration 1 is shown in table 8a. And even though this scenario is unlikely due to its simplicity before the sake of exploration, then we represented that a product set of these 3 random variables in table 8b. Looking at the table, we can see that all possible cases have been touched. The number of possible cases for test on, test bypass, and test miss are 2, 2, and 5, respectively, resulting in a total of 20 possible cases. When all these cases are covered, the coverage agent does not assign a value to the random variable. To prevent this, it selected the tests as case 1 and adds them to the regression suite to prevent incorrect prediction due to the lack of learning data. Case 3. Nevertheless, the incorrect random variables continue be at top of the contribution. To tackle this problem, the number of the product sets is compared. Cross coverage is composed to the product set of cover points, and in some cases, illegal bins and ignore bins may be used. Therefore, the number of product set of random variables must be equal to or less than the actual number of cross coverage bins that need to be filled. If the product set of the predicted variables is greater than the number of bins, it's an incorrect combination. In this case, it will be passed to the next combination in the candidate list until a combination that meets the condition is found. For example, if the total number of the bins for cross-test XY is 2,668 and the number of the predicted cases is less than 2,668, then it will not be the correct answer. Case 4. However, the incorrect prediction combination may continue to occur even though the number of the product sets be satisfied. Table 9 shows the random variables sorted by their contribution. In Table 5, which contains twice as many variables as required for class test XY, this is referred to a candidate list. The columns related to cross test XY, test X, test Y, and test on are highlighted. As shown in the Table 9, test on starts appearing from iteration 3 and in iteration 4. When prediction fails again, test on is not in the top 3, but it is included in the candidate list. When applying the coverage agent to the practical task, even though the data to be learned accumulates, there may be cases where the incorrect predictions are made for some cases. However, in all the cases we encountered, the correct answer remained in the candidate list even though the prediction was incorrect, as shown in iteration 4 of Table 9. Table 9, random variable candidate list for cross-test XY. In such cases, if the cross-coverage rate does not change for 2 regression cycles, the combination is no longer selected, allowing the next combination to be explored. Case 5. Random variables may have the same value but different names for convenience of writing constraint expression in the test bench. They can occur when they are ranked high together on the candidate list. This can interfere with the prediction combination, so it's necessary to make them so that only one remains in candidate list. As described above, various strategy enables the coverage agent to select a diverse combination within the candidate list. This is the reason why we insert twice the number of the prediction into candidate list. Chapter 4, Result. So Figure 6, comparison. Figure 6, comparison of the functional coverage rates with and without coverage agent. So Figure 6 compares the result of the original regression where the new approach was not applied with the result of the regression using coverage agent in terms of functional coverage rate. During the initial regression, 20,290 test cases were executed and the coverage agent was activated from the next regression. The table shows the exact numbers, and the second column indicates the number of tests created by the coverage agent for each regression suit. For comparison, the functional coverage rate of the original regression was calculated in proportion to the number of the tests created by the coverage agent. The second row of the second column represents the initial regression, which is not regression suit generated by the coverage agent. And the last row is also regression run to compare the figures with the original regression, so it is processed with a dash. After a total of 74,956 set tests, the regression with the coverage agent reached a functional coverage rate of 100%. In contrast, the baseline regression failed to succeed a 70% coverage rate even after the more than 100,000 runs as shown in the last row in the table. Figure 6. Comparison of the functional coverage rate with and without a coverage agent. In this work, the IP used has 134 cross coverages and 14,616 values as cross coverage mean. After first regression, 21 cross coverage were not filled, and the total count of their bins was 7,673. Figure 7 shows the process of remaining cross coverage rates being filled to 100% by the coverage agent, and the only 3 representative cross coverages are shown among them. So the cross coverage is 19% present the most ideal case where it successfully predicts using only the information from the first regression and reach to 100% in the next regression. So the cross-cover 14, on the other hand, continuously failed in predictions but gradually filled up as the number of regression tests increased, eventually succeeding in prediction and reaching 100%. In the case of cross-curve 7, its worst-case scenarios where prediction continue to fail and the coverage rate either barely increases or doesn't increases at all, even the number of regression tests, but it eventually reached 100% due to the strategies mentioned earlier. 5. Conclusion. Chapter 5 Conclusion. In this paper, we propose another approach using machine learning for functional coverage closure. We define the factors of the functional coverage closure challenging the cross coverage hole and fill them. The coverage agent utilizes the output generated during the regression process, thereby eliminating the need for DV engineers to manually analyze the holes and modify the constraint of random variables. As a result, functional coverage closure can be achieved markedly faster than the original regression without any additional effort from DV engineers. Okay, thank you for today. Thank you for your time. And today I read this reaching 100% functional coverage using machine learning, a journey of persistent efforts from DVCON2025. Thank you for your time. See you next time.